Hey everyone, and welcome to another exciting video lesson. Today we're going to talk about SOL G.3, where we're going to talk about pictorial representations and sort of start talking a little bit about formulas for distance, midpoint, and slope. The big thing about today's lesson, though, is we're going to talk about naming in geometry, segment addition postulate, and definition of a midpoint. So that's why we're going to talk about that G.3a right now when we talk about midpoint. So, naming in geometry. We have a couple different things that we need to talk about how to name. The first one is a point. So our definition of a point is that a point has no dimension or actual size. Even though we represent a point with a dot, it has no length, width, or thickness. They're usually named with one capital letter. Okay, and there's a typo right there, so you found a mistake, but that's how it is. So they're named with one capital letter. So on your paper you have 2 points. So this would be 1 point. And we would name it with a capital letter A. That's how we would name that point. It would be called point A. Or I could have another point, and I'd have to name it with another capital letter, and it could be point F. So points are only one letter, and it must be a capital letter. Next up are lines. A line is a collection of points. So it's all a bunch of points all put in a row. It is straight, it has no thickness, and extends in both directions without end infinitely. They can be named with a lowercase script letter or 2 capital letters, which come from points that are on the line. So the lines have a bunch of points all lined up, and they can all be named with 1 capital letter, so that's what we're looking for there as far as how to name that. Our first secret phrase today is sunny. Sunny. So we have 2 options on how to name these. Okay, so the first name would be with a script letter or a cursive letter, and we would just name that letter N. Okay, and yes, I know that looks like an M, but that should be an N in cursive. So, yeah, I think I'd say make an N in cursive, isn't it? Oh my goodness, it's been so long. I don't have italics, so, but that's how it will work. Usually they like to use the script letter L, so that's why we're talking about the script letters. And you'll see in a future video, we'll call it L1, L2, L3. So for line 1, line 2, line 3. For this one, you can name it with with the script M, or a cursive letter M. So that's how those would work for those names. That's the easy one. Here, we need to name it with AB. However, we can't just leave it alone with AB. We need to put the line on top of it. And we do need to put arrows on both sides, because that tells geometry nerds like me, and like you folks will be very, very soon, that it is a line and that it's continuing forever in both directions. So that's why the arrow's going on both sides. The same exact thing here for this guy, for MN. I need the line on top with the arrows on both sides. So lines go forever in both directions, and that's why we need the arrows on both sides, because the lines have arrows on both sides of them. So you can use 1 script letter, or you can use 2 capital letters. But make sure you put this on top so we know the difference. Next up is a line segment. A line segment, or sometimes it's just called a segment, is a part of a line and is bounded by 2 distinct endpoints and contains every point on the line between its endpoints. They are named by 2 endpoints with capital letters. Now this one, you only have 1 choice, so we're not going to use the script letter like we did for a plain old line. Now notice the difference that these don't have arrows on the end, because they are actually set in stone as far as where it can be. A plain old line, we can't measure how long it is because it goes forever in both directions. A line segment can be measured. So that's why we're going to talk about later on in this video about the segment addition postulate and everything else for that. Line segments are used to make all of our geometric shapes, so that's why it's important to know that. This guy would be called AB again, but this time I need to put a line on top. And because neither side has an arrow, then we don't put any arrows on the line on top. So when I see this, I know that that means line AB. If I see this, I know that that's line segment AB. Second secret phrase, Lorenzo. Lorenzo. Same exact thing works for this guy. So CM with one line on top. Now similarly, I could call this guy BA, and it would be the same exact thing. And I could call this one MC, and it would be the same thing. And the same thing back here. I could say B or AB or BA with the line with double arrows on top, and MN or NM with double arrows on top. I don't have to go in alphabetical order. Okay? And sometimes, depending on how things are named in the future, you'll see I cannot go in alphabetical order. Sometimes my order is already determined for me. So that's for a line segment that we have to know to just put the plain old line on top. Now for array, it's a portion of a line which starts at a point and goes off in a particular direction without end. They're named with two capital letters, but the first letter must be the starting point of the array. So where for the line and the line segment we could go both ways, this way we could call it CM or MC, and this one we could say MN or NM. For the rays, I am stuck with how I need to name it. So for DF, that's exactly how we would have to name it, D to F, and because there's only one arrow at an end, that's how I need to do that. So I'm going to draw a line and put one arrow. And that tells me that this ray starts at D and goes for F and keeps going on forever past that letter. And the same exact thing's true for here. I could say AB with a line with an arrow on one end, because it says it has a definite end point at A, and then it goes past B and keeps going on forever. Now, if we had something that looked like this, where we had this ray, and this was a C, and this is a P, okay? I still start with my endpoint, so my endpoint is C, then it goes to P, and I would still draw the ray in the same direction. So we don't need to flip it and name them in order there. I just need to make sure I start with the one that is my endpoint, and then I can keep going forever in that direction. So that's what I need to make sure I pay attention to. Now notice that DF and FD would not be the exact same thing. FD for this example would start here at F and then go forever in this direction towards the wall, okay? Instead of going in the opposite direction for D to F. So make sure you guys know that the rays are not the same forwards and backwards. The rays have a particular way that you have to name those. Now angles, we'll talk about a little bit more later on, but an angle is the figure formed by two rays or line segments. So that's why I said we use the line segments for when we try to make our polygons later on. They're called the sides of the angle. They share a common endpoint called the vertex of the angle. Angles can be named by one capital letter, which would have to be the vertex, but they're usually named with three capital letters with the vertex in the middle. And it's for this stuff right here why we're talking about this. Because when we see our angles, everybody wants to say angle B and be done and be able to move on. But as we'll see in a couple examples pretty soon, that won't be an option anymore. And I'll make sure I point that out to you. So that's why I tell you in this direction, I want you to name the angles in three different ways. Okay? Now that's what this symbol here means. It means angle. Okay? And you'll see it in a couple different ways. I always draw my angles like that, but our textbook sometimes might use that instead. And you might even see somewhere as well that with a little line there to see what's going on there. Okay? They all mean the same exact thing. It means angle B. Again, I will always use this one because if I get in a hurry, sometimes that can look like the letter L for me. And this one, I just don't care to use, but I at least want you to know that it's there for in case it shows up somewhere. So I'm asking you to name this angle in three ways. So angle B is a perfectly valid way to name this for right now. But now we also need to name it two more ways. And this is where this is going to come into place. We're usually named with three capital letters with the vertex in the middle. So the vertex is angle B. Or sorry, point B is the vertex. Because it's the one that's in the middle, it's where those two lines or those two rays meet. So I can name this A, BC. So angle A to B to C, where the vertex is in the middle. A to B to C is this angle right here. Okay, so that's telling me that's how it is, that's what that letter is. Now that's the second way. The third way I can name it is to call it angle CBA. So C to B to A is again the same exact angle with vertex B in the middle. Your vertex must be in the middle of the three letters. If I called that angle BAC, it would be a completely different answer. It would be a completely different angle. So we have to make sure we use the vertex in the middle. Okay? I'm actually going to leave this one for you folks to practice at home and name that, because this is an extremely important part of today's lesson, believe it or not. It might sound easy right now, it might sound stupid, but this is how they're going to name these angles on our SOL, and sometimes we get confused of what angle they're asking for. So that's why knowing how to name these angles is extremely important. Planes. Not airplanes, but a plane in geometry. A plane is a flat two-dimensional surface that is infinitely large and has no thickness. A plane must be named with three non-collinear points that lie on the plane. And this one wants us to name these planes. So I need three non-collinear. Non-collinear means they cannot all be in a straight perfect line. Because if you name them all in a straight perfect line, you could just be naming a line. So that's why they have to be not on the same line. So for this plane, I can name this one a bunch of different ways, so we'll name it quite a few. So I can call it AD, and then I need another point not on that line AD, so I could say F. I could call it ADZ, because those three lines technically aren't in the same line. I could call that DZF, okay, because I have DC and I have F. We could call it DZA, but it's the same exact thing as here, but it is another way to name it. So that will work, okay? I could call it ZFD, which would be the same thing as this one, just with the letters rearranged. Doesn't matter. Or I could call it ZFA, okay? These two, and then that third side. Looks like I could do AFD, which I already have, but it just changes my letters. And I could do AFZ, which again I probably already have, just a different order. You don't need to name it all of those ways. I just need you to see one, but these are all possibilities. Okay? So see how many of you folks can come up with this situation over here, but remember, they cannot all be in the same line. So what that means is that if I had another point, let's say right here, and I called it X, I'm just making it up, you could not name that ray TPX. Okay, so we can't have any TPX reports. We'd have to call it TPM or TPC for a TPC report to see what's going on there. So T to P to X would work, so that's, or would not work, because they're all in a straight line. So that's what we have to be careful of. Your third secret phrase, carmine. Carmine. Now right here, an example of a plane would be a shadow. Okay? Your shadow is a two-dimensional figure because it has no thickness, okay? And it's, I mean, your shadow really isn't infinitely large. It sort of is bound by certain points. But at different types in the day, it could be a very long shadow, it could be a very short shadow. So it will change throughout, so it can fluctuate. So that's our example of what a plane would be that you would see in real life. Is it has to be a two-dimensional figure, okay, and it has to be infinite in size. Now, down to some really good stuff. Okay, now we're going to start talking about some algebra. We're done with the naming stuff, and we could talk about this. Segment addition postulate. Now, this will only work for line segments, because remember, a line is forever, so we can't put stuff together for a line. An array has a certain starting point and goes on forever, so we can't add a bunch of stuff for there either. But the segment addition postulate says that if, and that should be an F there, so that if B is between A and C, then AB plus BC equals AC. All that you have to really remember is that the parts add up to equal the whole line segment. The parts add up to equal the whole line segment. So I'm talking about A, B, and C up here, but here I have D, S, and T. Now notice, it says that S is between D and T. It doesn't say that S is exactly in the middle, okay? It just says that S is in between. And if I look at this picture, it's not directly in the middle. I can see that. But what this is saying is that these two parts, so ds and st, have to add up to equal dt. Okay? So ds and st have to add up to equal dt. Another way to think about it is driving. Okay? If I'm driving from here to Disney World, okay, and I drive from Virginia to Georgia, and I take a break, and then I drive from Georgia to Disney World, okay? Is that the same thing as driving from Virginia to Disney World? Yeah, it's the same exact distance. So I cover the same amount of miles. It just depends on whether I want to take a 2-day trip or whether I want to take a 1-day trip. I still travel the same distance. So the two parts have to add up to equal the whole thing. Now, we need to read this, and it tells me that dt is 60. So that's important information that I need to use for this problem. So we're told that the whole distance from D to T is 60. And they might give us a unit there. It could be inches, it could be feet, it could be miles if we're taking a trip. It doesn't matter. But the whole line segment is 60. Well, when I write this out, all I really have to do is plug in. So I know that ds is 2x minus 8. I know that st is 3x minus 12. And the problem told me that dt is 60. And now we have an Algebra 1 problem, okay? Now that's the thing about geometry, is we use some rules and we use some properties so we can get back to Algebra 1. Geometry class is over at this step right now, ladies and gentlemen. This is an Algebra 1 problem. We are solving a multi-step equation. Something we learned last year in Algebra 1, and we were probably very good at it. So we have to get good at it again. It's no longer geometry, it's Algebra 1. So the first thing I want to do is combine my like terms. So 2x and 3x are both a like term, so I can combine them. 2x plus 3x gives me a 5x. Okay? Then I have a negative 8 and a negative 12. Well, negative 8 minus 12 gives me a negative 20. If you borrow $8 from me, and then you borrow 12 more, you owe me 20. Okay? If you're not sure about that math, you could always use your calculators in class and make sure you're dealing with those negative signs correctly. And then I bring down my 60. Okay? So I have to bring that down. Now it's a two-step equation. What do I move first? Well, I want to leave the x alone, and let's move that 20. So add my 20 to both sides. That goes away. I get that 5x's are, not a 1 there, sorry, but 5x's equal an 80. Now, I need to divide both sides by 5. And I get that x is exactly 16. Okay? Now, here's the difference between Algebra 1 and geometry. In Algebra 1, you're done with the problem. You found x, you're done, let's move on, I get to quit. But this problem is asking me to find x, find ds, and find st. How am I going to find ds and st? I know what x equals. And I know that ds is 2x minus 8. So how can I find out what ds equals? What's that? Plug it in. I like that idea. Yeah, let's try that. So I want to take this 16 that I found for x and let's plug it in. So 2 times 16 minus 8. Well, I know that 2 times 16 is 32 minus 8, and 32 minus 8 is 24. So I'm saying that ds is 24. Okay, 24 feet, 24 inches, 24 miles, meters, whatever you may want the unit to be. Okay? So let's check it again for ST. ST is 3x minus 12. And let's take that 16 and plug it in for x. So 3 times 16 minus 12. 3 times 16 is a 48 minus 12. And 48 minus 12 gives me a 36. Now, once upon a time in Algebra 1, this was maybe optional of plugging in. You have to do this in geometry. And we're going to see in a couple problems, I'm not going to ask you for x anymore. I'm just going to ask you to find the line segments. You have to find x to find the line segments, but you do need to find these in the last step. Now, you used to check in Algebra 1 just by plugging in and checking your work, but here we have an easier check. What has got to be true, or what had better be true, about these two numbers right here? They better add up to equal 60, because I'm told that that whole distance is 60 miles. So 24 plus 36, that gives me a 0, carry the 1, that gives me a 60. So they do both add up to equal 60. So if I travel 24 miles one day, and then I take a break, and then I travel another 36 miles, that's the same exact thing as traveling 60 miles. Okay, now 60 miles isn't that bad of a trip, but it's still the same distance. So from here to here, and taking a break, stopping for lunch, whatever it might be, and then traveling another 36 miles, is the exact same distance as just driving straight through. So that's all I'm saying here, is that the parts have to add up to equal the whole thing. Okay? Your fourth secret phrase, Jane. Jane. So, I believe this one's your practice problem. Now, pay attention that we give you something a little bit differently here. This time I'm giving you that ds is 25, st is 4x plus 15, and dt is 7x minus 8. Okay? When you're given information, label your picture. Okay? That's the very first thing that we should do, is if we're not given a picture, draw one. Or if we're given a picture that's not labeled, make sure that we label it. So make sure you always label that so we can start to see. So it's going to set up exactly the same as the problem I just did, where ds plus st equals dt. Okay? So that's what you have to look up for. I'm done because this is a practice problem, but I've given you a hint on how to set that problem up. Example number 2, definition of midpoint. Okay? The midpoint is the middle point of a line segment. That's why they call it a midpoint, because it's right in the middle. Since it's in the middle, since it is the middle point, then the two line segments formed with the midpoint and each endpoint must be equal. So that's what's going on here. They're telling me that C is the midpoint of AB. Does C look like a midpoint? No, it doesn't. C actually looks like it's not in the middle. However, if they tell me that C is a midpoint, it's a midpoint. This problem didn't tell us that S was a midpoint. This problem did not tell us that S was a midpoint. But this guy says C is a midpoint. Another way they can tell you that C is a midpoint is with slash marks, or sometimes called tick marks, where they say these two guys are the same. Stuff that's marked the same are congruent in geometry. So if I put 2 here, then I gotta put 2 here, because they have to be the same exact thing. So, stuff that's the same, stuff that's equal, stuff that's in the middle, we set equal to each other. So 2x plus 1 has to equal 3x minus 4. Okay? Now, another thing that I sort of want to go ahead and write down and say here is that AC has got to equal CB. And that's what I said up there, is that the midpoint to an endpoint. So A to C, C to A is the same thing. C to B, B to C is the same thing. Have to be equal. If C is in the middle, it's breaking that line segment exactly in half. So I know that those two things equal each other. I'm not told what they add up to equal because this is a slightly different problem. I don't know what they add up to equal, but I will find it out. Now notice for this problem, it doesn't tell us to find x. It tells us to find out what AC is, what CB is, and what AB is. But I need x to find those things. So, geometry class is over. It's an Algebra 1 problem now with equations on both sides. Now I need to get my x's on the same side. So I either have to move the 2x or I have to move the 3x. I would prefer to move the 2x, so